Thank you for coming today to this Harrington Faculty Fellow Symposium. My name is Adrian Buganza Tepole, and I have the honor to be one of the faculty fellows for this year. There's 3 faculty fellows and also 20 or so graduate student fellows. So the Donald D. Harrington Fellows Program was created by Sybil B. Harrington as a tribute to her late husband, and is the most prestigious fellowship program at the University of Texas at Austin. And like I said, it awards visiting faculty professorships for a year, and then also supports graduate students. So I'm very grateful for that's the reason that we can host you all here today for this workshop. And some of the perks from the program, if you are interested in applying. It's restricted, I think, for the faculty side within your first 8 years after starting an academic position. So if you are a junior faculty or have junior mentees, maybe ask me afterwards. There's also Marv here if you want to know a little bit more about the history of the program. And this is from they hold an annual symposium in Amarillo, Texas every year. So I got to fly in a private jet to Amarillo. That was one of the highlights. And yes, so this is from a couple of months ago. And yeah, so that's the program. So thanks much to that support, and also to the Oden Institute and the Aerospace and Engineering Mechanics Department, and my host Karen and Manuel, who were the ones that nominated me, that we can have this workshop. So thank you all for your support. And just a brief overview of the agenda, and then we'll remind you of things as we go along. This has been put together, special thanks to co-organizers, senior colleague Jan Fogg and junior colleague Manuel Rausch, who looks very young in that picture. And the event coordinator, Libby, who you've seen outside. I don't know where she is. But thanks to you all for helping us putting together this event. We have a very packed day, so we'll try to keep you on schedule. We have a couple of keynotes today. We have Professor Karen Wilcox, and then tomorrow we'll have Professor George Kaniadakis, and we have 2-hour sessions for the rest of the day and a social in the evening. Again, so we'll remind you, but because we have a very packed day, we'll probably try to stick to schedule. I'm ahead of schedule, so I think it's okay. And I think that's it for the agenda. And then I have the honor to introduce Professor Karen Wilcox, who's the director of the Oden Institute for Computational Engineering and Sciences. And before joining UT, she was the co-director of the Center for Computational Engineering at MIT. She has numerous accolades. She's a fellow of SIAM, USACM, a member of the National Academy of Engineering, a member of the New Zealand Order of Merit, the recipient of the Oden Medal from USACM, among many other recognitions that I would be out of time if I have to introduce a little bit more. So that being said, let's welcome Professor Wilcox.
Here it is. All right, very good. Okay, well, thank you very much, Adrian. It's really great to be here. First of all, I'd like to welcome everybody. For some of you, maybe it's your first visit to UT Austin. I think for a number of you, welcome back home. I know many in the audience were here at UT at some point during your graduate studies or postdoc studies, so welcome back. I want to give a special thanks to Adrian for organizing this symposium. As we just saw, these Harrington Fellows, I think it's really a wonderful, wonderful program. And Adrian, it's just been fabulous having you here for the year. We're going to miss you because you've been such a presence, I think, both in the department, in the aerospace department, but also here in the Oden Institute, coming to the coffee hours, coming to seminars, interacting with our students and postdocs. So it's really been a fantastic year, and we're very grateful to the Harrington family for the support that makes it possible. So maybe by now you've figured out that, I guess I should not stand there. Let's see if we can figure this out. Do I have to click on the screen to get the clicker to work? Okay, there we go. All right, maybe you've figured out by now that you're in the Peter O'Donnell building, which is the home to the Oden Institute. So the Oden Institute occupies all of this building. The Institute is probably familiar to many of you, but here's just sort of a snapshot of us. So the predecessor institutes, the first one, TICOM, the Texas Institute for Computational Mechanics, was founded by Tinsley Oden in 1973. So just a couple years ago, we celebrated our 50th anniversary, and it's really pretty remarkable when you think about what was going on in 1973, to think about the seeds that were planted that has led us to where we are today. Today, we're total close to 500 people. We have, in total, about 140 faculty who are affiliated with the Institute. 20-some of those, 25 of those are ones that the Institute has hired. The other 120 are faculty who are hired by departments and are affiliated with us. And those faculty come from 26 different departments across 8 of the schools and colleges across campus. So we really cut across a lot of campus. We have a couple hundred students, about 100 students in our own computational science, engineering, and mathematics program, and another 100 students who are graduate research assistants doing PhDs in home departments, but affiliated with the Institute, and many fabulous, fabulous programs. It's a little quieter probably today than it would have been if you were here last week or a couple weeks ago with the end of semester. But nonetheless, if you have time and you want to wander through the building, you are very welcome, and you will probably find graduate students, postdocs, and maybe even in some of the faculty. This is Peter O'Donnell Building, the Oden Institute. As soon as you go past the horse, you're in GDC, the Gates Dell Building, which is home to computer science. All right, so I am going to talk today about some of the work that we've been doing in digital twins. And to kick off the symposium, I'll tell you, first of all, this is a relatively light presentation. There's not going to be too much heavy math in this, but just at a little bit higher level. Talking a little bit about digital twins. I think by now everybody in this room presumably at least thinks they know what a digital twin is. And as I go through some of the introductory material, I hope to highlight where I see some of the research needs, particularly for the computational mechanics community. Then I want to talk a little bit about the work that has been going on in my group for some years, where we have been focusing on graphical formulations for digital twins, particularly as we start to think about scaling digital twins out to truly complex systems. And I'll show you a little bit of the work that we have going on, really drawn from very different domains, I think emphasizing the importance of foundations that cut across domains, and also the really exciting potential of digital twins. Okay, so I had the pleasure, the honor of chairing a National Academy study, a big study on foundational research needs and future opportunities for digital twins. The study report was released right at the end of 2023. And what I am showing you here is the definition that we as a study came up with in an attempt to really say what is a digital twin. And of course, there's not going to be any one definition that everybody will accept, but trying to come up with a definition that maybe reflects what a digital twin is and what it is not, particularly as we look across different domains. So I can read it here. A digital twin is a set of virtual information constructs that mimics the structure, context, and behavior of a natural, engineered, or social system or system of systems, is dynamically updated with data from its physical twin, has a predictive capability, and informs decisions that realize value. The bidirectional interaction between the virtual and the physical is central to the digital twin. So that last sentence is really important, and we added that sentence to really address this question of, is a digital twin is it just a new name for simulation and modeling, which is what you sometimes hear out in the community. Oh, we've been doing simulation and modeling for many decades, and digital twin is just advertising hype and a new name for that. One thing that really came through in this National Academy's study is that a digital twin builds on simulation and modeling, but it really goes beyond, and that bidirectional interaction between the physical and the virtual is a key part of that going beyond. And so this figure from the report really tries to emphasize that where on the right here, the virtual representation, this is the modeling and simulation, whether it's our tried and true physics-based mechanistic models, whether it's machine learning, AI, generative models, whether it's a combination of the two. But that's just one piece of the digital twin. What's really important are these flows from physical to virtual. This is the inverse problem, or the data assimilation problem, where data acquired in the physical world are assimilated into the virtual representations, so that the virtual representations have that dynamic, updating, personalized aspect to them. And then the flow from virtual to physical, where now the virtual representations, the models, are used to bring about change in the real world, either through control or maybe through some kind of optimal experimental design problem where sensors are moved or data collection is adjusted. Then, as I said, bringing back change in the physical world, and then sort of this back and forth. And so as we look at this picture, already we see huge roles for computational mechanics and for scientific machine learning, not just in the models, but in these flows, in the optimal control, optimal design, optimal experimental design problems, and in the inverse problem and data assimilation, which, by the way, need to be done not only at scale, but often in real time onboard a system in situ where there may be computational constraints. And then finally, before we leave this chart, I want to draw your attention to, first of all, the humans in the middle, that yes, many digital twin applications will be automatic or autonomous, but there are probably many more situations where we need to be thinking about the human in the loop, meaning that the tools we develop need to be interpretable. We need to be thinking about visualization, communication of uncertainty, all these really important topics. And then finally, the loops going around the outside, the topics of verification, validation, uncertainty, quantification, security, privacy, ethics. These are really, really important topics that as we start to talk about virtual representations, models that are coming off the researcher's computer or off the designer's computer to be out in the real world, having continual and dynamic effect on the real world, we need to be even more concerned about all of these topics than maybe we have been in the past with modeling and simulation. So when I look at this graphic, I actually see decades of works for the computational mechanics community that takes us from powerful modeling and simulation to this vision of digital twins that bring value. I'm going to keep going the wrong way on this thing, which is reverse. We'll see if I'm the only one. As I think about a digital twin, I think often, maybe not for people in this room, but for many people, the core of a digital twin is data. We keep hearing about AI and data and all this data. This sense that a digital twin is built on a core of data with numerical models, analytics, machine learning, and decision-making wrapped around it is a reasonable conceptual model in many cases. But there are, there I go again. Okay, let's go this way. But there are many, many applications, particularly as we start to look at digital twins in the physical world, in the natural world, and in the biological world, digital twins of human patients, digital twins of planet Earth, digital twins of complex engineering systems, where even if the data are abundant, the data are not nearly enough to be characterizing the complexity of the situation, and not nearly enough to be issuing predictions about the future that we haven't seen yet. So in those cases, we really need to be thinking about a mathematical model as the core of the digital twin, with the data now coming in through the lens of those models. Again, this is mathematically what we call an inverse problem or a data assimilation problem, and then the decision-making wrapped around that. So it's not that one of these is right and one is wrong. They're just different ways of thinking conceptually about the digital twin. And as I go through the examples, you'll see that most of what we do, we have the model at the center when we're working on engineering systems or biomedical systems where we have governing equations that we really want to be at the core of the digital twin. But there are some cases where we don't have good mathematical models, and the education example that I'll show you is one where we have a very data-centric view of the digital twin. I I emphasized this on the other slide, but just to double down on it, and also especially to the young researchers here, VVUQ, verification, validation, uncertainty quantification, have always been absolutely essential as partners to the development of sophisticated modeling and simulation technologies. As we think about digital twins, these topics are even more important, right? Come back to what I said. We're talking about letting these models go out into the wild and bring about changes on a dynamic and continual basis in the real world. We better be sure we understand what they're doing, when we can trust them, and what the limits of their validity are, how much confidence we have. And what's more, as we think about, and here are the definitions from I think a 2012 NRC report of what is verification, validation, uncertainty quantification. What's more, as we start to think about digital twins, not only are VV and UQ critically important, they also bring about new challenges, because how do you validate a model if you're going to have something in the loop, whether it's a more classical data assimilation or whether it's something built on scientific machine learning, something in the loop where things are going to be changing, where you're going to be acquiring data and you're going to be adapting the models that underlie the digital twins. How do you validate in that context? And how do you do all of this validation, verification, uncertainty quantification, again, onboard dynamically, perhaps in real time, computationally fast enough so that you can not only issue those controls, but also do it with the confidence that you would need if you knew that someone's life was at stake. This is an absolute grand challenge for computational science, and I think a really, really important area of future research. All right, last just sort of general thought on digital twin, and it relates a little bit to the topics of VVUQ, which is this question of how detailed or how high fidelity does a digital twin need to be? And if you stop people on the street and ask them, you'll get a range of answers, and we saw this through the Academy study, that some people will tell you a digital twin is only a digital twin if it is an exquisite, high-resolution model that models an aircraft down to the very last rivet. And somebody else will tell you a digital twin is only a digital twin if it's a surrogate model that runs in real time. And so those are kind of the two extremes, and then you could hear everything in between. What we concluded in the National Academy's study is that actually a digital twin should be fit for purpose. In other words, you have to think about what are these decisions that you want to drive, how much fidelity do you need, how good is good enough, what available resources and acceptable costs do you have, and actually the answer to that question of what does the digital twin look like in terms of fidelity and resolution is a trade-off among all those things. And again, that sort of feels high level and philosophical, but this is actually a big mathematical research challenge, because in order to assess whether something is fit for purpose, you need to be able to assess its fitness. And then you're getting back now to how do you quantify the uncertainties? How do you understand verification, validation? How do you understand where assumptions will fail? And how do you do that in this situation where everything's going to be changing dynamically? So again, I could talk for a long time about these things. We've seen research along these lines in our field if we look at a posteriori error estimation and how, for example, that has been used to guide adaptive grids. Right? This is sort of maybe we could say narrower, more mathematically well-defined example of what it means to be fit for purpose and to control the fidelity based on needing to estimate certain quantities of interest. How do we take that kind of rigorous thinking and bring it over to the digital twin setting? Again, I think that is really a grand challenge. Okay, so all of that was sort of general thoughts and some of the findings and outputs that came out of the National Academy's study. Let me now transition into talking about some of the work in my research group. And I'm going to focus today more on the formulations than the methods. We do a lot of work in the methods that enable everything I've just been talking about, particularly reduced order modeling methods and multi-fidelity methods, which really are getting at these computational costs questions of how you can solve an inverse problem or a data assimilation or an optimal control problem in real time. I'm not going to talk about those today. I'm going to talk about the way we formulate digital twins, and particularly how we build uncertainty quantification from the very beginning into our digital twins so that we are setting ourselves up to address these really important questions of verification, validation, and uncertainty quantification. So let's start with like graphical models 101. This is Michael Jordan's 1999 book on learning in graphical models. And I just love this quote. Graphical models, a marriage between probability theory and graph theory, provide a natural tool for dealing with two problems that occur throughout applied math and engineering, uncertainty and complexity. Fundamental to the idea of a graphical model is the notion of modularity. A complex system is built by combining simpler parts. Probability theory serves as the glue, whereby the parts are combined, ensuring that the system as a whole is consistent and providing ways to interface models to data. So Michael Jordan could have been talking about digital twins, but this was in 1999, and the phrase digital twin really was coined around 2010, 11 years later. So as we look at this and we draw out these words, we see so much of what I was just emphasizing as being the central concept of how a digital twin goes above and beyond just being simulation and modeling. Those connections of models to data, this management of complexity, this management of uncertainty. And what I think it's really important to recognize with a graphical model is that when you build a graph, you have nodes and you have edges. The nodes are entities, they're things, and the edges represent relationships among the things. And what's really key in a graphical model is that relationships are just as important as entities. And this, of course, I think translates into the mathematical framework that we need for formulating digital twins. So in my group's work, we use a multi-layered graphical formulation to manage complexity and embed uncertainty quantification. By multi-layered, we think depending on the problem, in some cases we need to build a knowledge graph as the foundational layer. I'm not going to talk too much about that today because when it comes to problems in computational mechanics, we don't necessarily need the knowledge graph because we actually have a fairly well-defined mathematical model, going back to those bullseye pictures. But in many cases where you don't have a very nicely well-defined mathematical model that you can write down the governing equations and the boundary conditions and the initial conditions, you need to think about even how to architect the digital twin, and that's where knowledge graphs come in. I will show you one if I get to it on the educational work. I will talk a little more about the predictive layer. So this is the layer in the middle. So this is where we want to represent the digital twin as a graph, and really importantly, we want to embed uncertainty. So I truly believe that even though it makes the problem more difficult, building deterministic digital twins and then worrying about uncertainty quantification afterwards by somehow, I don't know, putting some giant Monte Carlo sampling loop around it and pushing the button and then coming back in 10 years to see whether you got an estimate of the mean, that is not going to get us there. We have to be thinking about uncertainty and baking it into the way we architect, we conceptualize the digital twins from the beginning. And so we do this using probabilistic graphical models. What's a probabilistic graphical model? It's a graph where the nodes are random variables, and so now the edges in the graph that represent the relationships between the random variables are conditional probabilities. So let me show you. This is a little bit older work, but it's still the foundation for what we're doing and what we're using in the group. So this is Michael Kapdane's PhD work. Michael was actually my last PhD student at MIT. He graduated after I had already moved here. So what does a probabilistic graphical model look like? We first of all think about the physical space, and in the example I'll show here, that might be an aircraft, where we want to represent the state of the physical system. So what is it that we're trying to track? And in this example, this might be a digital twin for structural health monitoring. So we're really interested in characterizing the structural health of the aircraft. But you could imagine that if this eventually one day is an all-aircraft digital twin, it's not just the structural health, it's probably also the propulsive system's health, everything you could probably imagine, everything you could imagine about the aircraft. So mathematically, we're representing these. I think the pointer doesn't work on the screen. Mathematically, we're going to represent the state here at discrete times, T0, T1, T2, as random variables, the random variable S. What we're looking at here is the evolution of the physical state in time. And so now the edges in our probabilistic graphical model, that edge there from S0 to S1, represents the transition from one state to another. And again, mathematically, that is the conditional probability that you see there. In the digital space, we're going to define the digital state. So these are now the parameters. And in a model-centric view of our digital twin, we have a mathematical model. These digital states are going to be the parameters that characterize the digital twin through the lens of our model. So these may be positions, velocities, pressures, temperatures, kind of the classical state variables, but also things like the material properties, the Young's modulus, all the parameters that are needed to define that mathematical model. And again, we can think about that digital state evolving in time, and we can think about the graph representing the transition of the digital state. We can introduce the observations. What are the data that we can acquire, whether it's on board from sensors on board the aircraft, or whether it's physical inspections, flight logs and things that lives in the physical world. And again, we can start filling out the graph. What we're looking at now is an inverse problem. Given partial and noisy observations, O, of a not directly observable physical state S, can I characterize the digital twin, the digital state D? So we're seeing in the graph here a formulation of the Bayesian inverse problem. We can add in the actions. What are the control actions I can take? Again, those live in the physical world. We could add in quantities of interest, things I may want to predict, particularly as I am making decisions about optimal control. We can add in the notion of a reward function or an objective function. What is the objective by which I'm going to make these optimal decisions? And we can keep building out a graph. And don't get too caught up on the particular topology I'm showing here and which arrows are going where. But the idea is we can characterize the digital twin, its models, the digital state, the observations, the data, and then the decisions represented by the actions and the rewards. And we can architect it as a graph where we're encoding uncertainty and we're representing at a prominent level the relationships among all the pieces. We can also think about extending the graph out into the future. So now we're talking about prediction, where these actions, U3 and U4, are in the digital space because they haven't yet taken place. So this is a planning or optimal control over a future horizon problem. So what is the graph? The graph is nothing but the giant joint probability distribution that represents the relationships among the digital states, the quantities of interest, the rewards, and the future actions, all conditioned on what you have seen, the data that you've collected in the past, and the actions that you've taken in the past. And once you think of the digital twin in this way, and by the way, statistics was probably one of my I think it was my second least favorite class as an undergrad. So it's sort of ironic for me to say, let's think about the digital twin as a giant joint probability distribution, because probability distributions just don't have a good, neat place in my brain like linear algebra. But nonetheless, we want to think now mathematically of the digital twin as this giant joint probability distribution, conceptually. And now that we have that mental model of the digital twin, now we can come in and think about our data assimilation, prediction, optimal control, learning, all the different tasks for the digital twin updating, for issuing the predictions, for making the decision making. We can think about all those tasks as lighting up different parts of this giant joint probability distribution where, for example, if you're doing a data assimilation problem, even within that, you could decide whether you're going to use a filtering algorithm or a smoothing algorithm, and that's going to determine how much of the past states or past data you are using when you're doing your assimilation at each step. And so all these different tasks are now going to manifest in accessing different parts of the joint probability distribution, and then in turn now comes the numerical methods where you decide, I want to use a classic optimization under uncertainty approach to solve the optimal control problem, or I would like to use dynamic programming or reinforcement learning. I mean, whatever algorithm you want to sit on top of that. Okay, so in Michael's thesis, he developed this framework and we applied it in the context of structural health monitoring for an unmanned aerial vehicle. We still have the vehicle in my group. Let me go over this. So again, sort of the older works showing how the PGM, the probabilistic graphical model, forms the foundation, and then for this particular vehicle, we were able to show how you could acquire strain information on the wings, on board during flight, assimilate that strain information, do updating of the digital twin, and then use it for dynamic mission replanning if you had a vehicle that incurred some kind of structural damage while it was flying. One of the pieces of work that we've been doing more recently in the group is coming back to one of the challenges of VVUQ, and that's the challenge of verification. So verification of cyber-physical systems, verification of digital twins, again, is a huge, huge challenge, and this is verification now separate from validation. There is a vast literature for cyber-physical systems looking at verifying. I mean, of course, this is something that is done for all aircraft flight control systems, anything that is on board and operating on an aircraft. As we start to think about digital twins, what does it mean to verify a digital twin? And if we go back and we start to ask the question of how is a digital twin different to what has been done in the past, this idea that we're bringing many different pieces together and that things are going to be dynamically updated, as I said earlier, this leads to new questions in the verification. And one particular question that rises is this question of synchronization. So what happens if you have these data streams coming in, if you've got the digital twin and it's updating, and then think of the example I just gave where we've got some kind of a structural health issue going on board. We're acquiring data from the sensors on board the wing. The digital twin is updating its estimate of the structural health and then issuing commands for dynamic mission replanning. What happens if the sensor data comes in out of order? What happens if one sensor reading gets delayed and you just don't get it? Then what happens? This is where verification comes in, because you have to be able to make some level of guarantees of what is going to happen if, in all these different situations. So this is where the field of formal methods comes in. And my student, Luan Huang, who's a PhD student here, she's doing a PhD in computer science here at UT, has shown how we can now take the probabilistic graphical model. And remember, we started with the PGM because we wanted to provide this foundation to sit our Bayesian inverse problems and our optimal control problems on top of this formulation that encodes uncertainty. So Luan has shown how we can now take this same PGM and use it to construct a finite state machine, which basically is something that's going to lay out all the possibilities, all the different states that the digital twin can get into, and then apply TLA, the temporal logic of actions, which is kind of the workhorse method that people in the formal methods community use to go through and do the formal model checking. And I'm not going to go into the details, in part because it's a whole lot of computer science stuff that is definitely less comfortable for me, and I expect for many of you here. But there's a way to augment the probabilistic graphical model. In particular, we can't just have this mathematically abstract view of what's going on, because if we take, for example, the sensors, here it's just it's a random variable, O sub t, but there's the data that's actually generated in the real world, and then there's that sensor reading that has to be transmitted in some way to something, and that actually brings the sensor reading into the digital world. In other words, we need to duplicate nodes in the probabilistic graphical model and recognize that there are now edges that are representing things like transmission, maybe over a Bluetooth sensor network, which, by the way, could be corrupted, could be adversarially affected. So modeling all those kinds of things and all those delays in the system. All right, but again, maybe the key message here is the graph is the enabler, because once you think of the digital twin as a graph, you can now start to architect the graph so that not only are you embedding all the models the data and the decisions and all their connections, you can also start to look at information flows between this and this modeling this bidirectional interaction between physical and virtual, and have the graph connect to things like TLA, where you can start to ask questions about verification. Okay, now let's see. I'm grateful that Adrian gave me like an extra 7 minutes, but I'm going to fly through a few examples, and along the way with these examples, I'll kind of give you a sense of some of the methodological questions that we are asking and trying to answer, where we're trying to push the methodology on digital twins. Yeah, our interest is really in methods that cut across domains. But what we've really been finding in the last few years is that every time you engage with a new collaborator in a different application domain, all kinds of interesting and new questions show up. And sometimes those questions actually do have analogies in other domains. Often they're domain specific. And so I hope to highlight some of those interesting methodological questions for you along the way. So I'm going to start off with some of the work we're doing in digital twin-enabled spacecraft operations. So in particular, we're thinking about autonomous on-orbit spacecraft servicing missions. And so the general setup is that we have a target spacecraft. So this is the one on the inside here. And for some reason, we need to get the chaser spacecraft to come into orbit, to rendezvous, ultimately to dock, and maybe to do an on-orbit either repair, refueling mission, or maybe the target is being decommissioned and the chaser needs to come in and grab it and then tow it away into some other orbit where eventually, I don't know, did the Russian spacecraft come down safely? I didn't see. I saw the news where it was going to come in and they had no idea where it was going to land. Or you thought, oh, it's good, I hope it's not going to be anywhere near. Anyway, so this of course is a very big need right now. There is so much stuff up in our Earth orbits, including a lot of spacecraft that are going to need to be serviced, refueled, and or decommissioned. So clearly this is a fantastic use case for digital twins, because particularly if we're thinking, for example, about an on-orbit servicing mission, we have a spacecraft that's up there that's got something wrong with it, and having a digital twin where you can be acquiring data, and by the way, the data that you have here are really are not nearly enough to go and train your favorite neural network, because the data you have are going to be some combination of Earth-based observing, where you get glimpses of what the spacecraft might be doing, from which you're going to try to back out what might be going on board, and maybe some kind of data from the sensors that are on board the spacecraft that might be able to transmit and maybe be acquired as things go on. So having a digital twin where you can have your best guess of models, where you can assimilate data, you can update that digital twin as this chaser's coming in. You could imagine, and we want to be continually updating the model of what's going on with the target aircraft, so that eventually when we do the rendezvous and the docking, we can execute things effectively. So this is a really rich problem. It's a rich problem not just because of the sparse data and the extreme uncertainty, but also because the different level of physics that are needed. The figures here don't really capture it, but in this pre-capture phase, what we're looking at here with the orbit rendezvous, we might be looking at the scale of many kilometers. But then as we come into the capture phase and eventually where the two spacecraft are going to dock, this is all of a sudden a situation where the contact mechanics are really, really important. And over here where you're using your ODE lump parameter models, that's great and that works, but the moment you start coming in and talking about the actual rendezvous and the docking, you've got to have detailed computational mechanics models that capture the contact mechanics, because if you don't, you're not going to get things right. So it's a problem that also has multiple physics, multiple levels of resolution. So Sebastian, who's sitting right up there at the back, I think I don't have my glasses on, yes it is Sebastian, is a PhD student in the Oden Institute CCM program working on this problem. And you're going to see a common theme here, which is the starting place is think about what the probabilistic graphical model looks like in this setting. So we go through, we identify the physical states that we want to track in this asset twin space system, the digital twin states. What are the models we have available? How are those models parameterized? So how are we going to represent the digital twin in the virtual space? We think about the data. As I already said, there's limited data, but some of the data comes from sensors on board the vehicles. Some of the data comes from off-vehicle sensing. And by the way, I didn't mention this, but sometimes this target might not be a friendly target. This could be also an adversarial type capture, in which case the data that you have is whatever you're able to acquire from the outside looking in. Thinking about the quantities of interest and the rewards, and then also thinking about the control actions that you would have at your disposal. So we architect all of this as a probabilistic graphical model. And then in terms of thinking about the methodologies and what some of the research is that is needed to build digital twins that are appropriate for a system like this, one of the key things that Sebastian is looking at is how do we build modular digital twins? So let's dig in a little bit more to this particular example and think about the pieces. And if we think just about that first rendezvous phase, we're going to have model for the kinematics of the target spacecraft. We're going to have models for the kinematics of the chaser spacecraft. And we might have a model of the propulsion system for the chaser. And then you can see there in the flow of the diagram, all the different pieces of information that are built in those different subsystems. So when we're building a digital twin, what could we do? We could draw a big sort of box around all of that, put it all in the box and say, okay, I'm going to build a digital twin of this target chaser system and have a monolithic digital twin where all the models are tightly coupled inside. And now I'm going to think about the data assimilation, the optimal control kind of wrapped around that. That is something you could do, but then the problem is you've now got this monolithic digital twin. And if you start to look at the way that modeling and sort of operation of assets takes place in the digital world, you recognize that that monolithic approach is actually probably not the right way to go. And so instead, what we're looking at is, can we build a digital twin that somehow maintains the modularity? In other words, could we build a digital twin for the target kinematic subsystem, build a digital twin for the chaser kinematics subsystem, build a digital twin for the chaser propulsion system, recognizing that it's probably different groups, and as I said, these assets may not even be owned by the same entity. So keep the digital twins sort of separate, but now we have the problem of the coupling and all this information flow between them. We have to manage all of that as we are now doing the digital twin updating or the solution of the optimal control problem. And so this is where Sebastian's research work is coming in terms of understanding how to develop modular and scalable methods that let you manage the digital twins in this modular way while preserving the integrity relative to if you did it all at once. And there are many research challenges in here. And I think the analogy here is all the work that has been done in multiphysics coupling, right? Where go back to fluid structure interaction, where you can do a tightly coupled fluid structure interaction, or you can do the looser couple where you have a fluids code and a structures code, and then you need to really worry about how you manage the interface. We know you can't just pass information back and forth and hope for convergence. Another example would be domain decomposition, where we take a complex domain, partition it into pieces, and then really have to think about how the interfaces or the boundaries are managed and what this means for the convergence of the overall simulation. So again, a lot of analogies in our history of computational science, but new challenges that we need to tackle in this modularity. The second example I'll give, and I'll go a little faster, is some work that we are doing together with the Center for Computational Oncology here in the Oden Institute on digital twin-enabled cancer treatment. So Anirban Chaudhuri, research scientist in my group, and Graham Pash, I think Graham's here, I didn't see him, a PhD student here in the Oden Institute. And again, vastly different system to the space systems, but again, the story is kind of the same, which is you can acquire data. And by the way, the data that you can acquire for a cancer patient, yes, those MRIs are big files, but the amount of data that you're acquiring is so sparse, particularly in time, that you cannot just use the data to try to build a data-centric digital twin. You've got to have models. We can acquire data, we can assimilate that data into our mechanistic, PDE-based models. Uncertainty, also incredibly important in these settings. Build the digital model and then use it to issue predictions and issue personalized or adaptive control through both treatment and also on deciding when to acquire new images. So again, we can look at the probabilistic graphical model. We can lay out, oh, that Q got kind of, okay. The Q is trying to be a brain slice. I shouldn't trip over that, which is, it's kind of an interest that AI has been at work there. That's kind of funny. Anyway, we can lay out the physical state, the digital state, the controls that you have, the quantities of interest, all those elements of the graph. And again, really essentially build in uncertainty from the beginning. All the methods that we use here are Bayesian, so yes, we have to come up with priors, but baking in uncertainty from the beginning. So Graham's work has really been trying to build out this Bayesian framework for the cancer patient digital twin at high fidelity. At the core is our mechanistic model, so a reaction diffusion model. This is where we work with Tom Yankelov's Center for Computational Oncology and leverage all the great tumor modeling work that they've been doing over the years. Thinking a lot of issues around the imaging data and how you manage all the different modalities, kind of putting all that together and doing it at large scale so that we can think about building these digital twins for full three-dimensional representations, in this particular case of, this is a glioma in the brain. So Graham will probably be buzzing around today. If you're interested in some of the work that he is doing, you can see here the elements of how he's putting it together with Phoenix PETSI and then HippieLib for the inverse problems. Everything is done fully with adjoints so that we can get sensitivities. This is the only way to truly enable that uncertainty quantification at the scale we're talking about here so that we can characterize uncertainty. Maybe just one highlight. I mentioned everything is done with adjoints. So the Hessian, of course, provides a critical role in the inverse problem, and I know Omar's giving a talk later today, and I'm sure he will talk about Hessians. The Hessian is not only telling you, characterizing the uncertainty associated with the parameters you're estimating in the inverse problem, it also is giving really valuable information that tells you how much value would there be in an additional image. And so in this particular plot here, we're looking at the eigenvalues of the Hessian and asking the question, if we were to bring in this patient, the sick person, and image them daily versus weekly versus fortnightly, how much additional information would that bring in terms of our ability to calibrate the digital twin, to drive down the uncertainty, and then translate that into predictions and ultimately into treatment decisions. And of course, what's beautiful is that it's not just the eigenvalues and the decay that tell you about information gain, but the eigenvectors that actually give you a sense of what kind of uncertainty is manifested, in this case, in the parameters of that PDE model. So there's a lot going on there. All right, in the last maybe just 5 minutes, I'm going to jump to something completely different. And so there's going to be no conservation of mass, momentum, or energy in this one. But this one's exciting in part because it's an application that I think is very important, that I'm very passionate about, but also because I hope it highlights to you how this graphical representation is incredibly powerful because it's going to be the same underlying PGM representation. So this is also part of Luen's PhD work, where we are thinking about modeling student pathways and asking the question, could one build a digital twin of an educational system, again, to take data, to update our understanding of what's going on, to issue predictions, and then to use that to drive decisions that bring value. So yet again, we reach for the probabilistic graphical model. We've got the states, the controls, the rewards, the quantity of interest, the observational data. They are vastly different now because now we're not talking about sensors on board an aircraft or a spacecraft. We're not talking about MRIs. We're talking about things like grades, attendance records, institutional records, but nonetheless, we can put it all into the language of the probabilistic graphical model. We've been particularly looking at educational pathways. So this is time-dependent student behavior. And we have been working with the state of Texas, so the Texas Higher Education Coordinating Board, to look at academic trajectories for transfer students. So these are students who start in community colleges and want to transfer into four-year institutions like University of Texas at Austin. This is completely notional, but just to give you a sense of what we are talking about here, these are, for the most part, not students who start off in community college, cleanly complete 2 years, pass all the classes, and then make a smooth transition into a four-year institution. These are students often who are sometimes coming in with not meeting requirements. There are Texas requirements in reading, writing, and math, often not reading requirements, particularly in math, for whom classes like college algebra are huge barriers to progress, for whom other things are going on in life so that they have semesters where they don't enroll. And so in this just sort of sample trajectory, right, here's an example of a story we might see. So, you know, what could we do about this? We can think about all the data that is collected, and there is so much data that's collected. Here's the very sad part of it. All the data is collected and it's all stored in text files or the equivalent of Excel spreadsheets or, if you're lucky, R, things that can be read by R. But so much data, and maybe I won't go through all of this. If you're interested, please talk to me. Everything that I'm showing you here, you could find this. This is all public. The way these different reports, they've all got different numbers. I forget what this one's called, CMB 001. That is storing in different places demographic information about the students, what they're doing at different institutions. You can imagine all the different kinds of data. Okay, so what could we do here? We're going to try and build a graph. And this is an example coming back to something I said earlier where, fortunately, we don't have conservation of mass, momentum, and energy. So we have to start at that bottom layer of the digital twin. And we start with building a knowledge graph. And so the very first question we asked, and Lewin and I have been working on something related to this for about a decade, how could you model an educational system as a graph? What would the nodes be? What are the entities? So we've built up this graph where nodes are things like students, institutions, courses, academic readiness, and the edges represent the relationships between those entities. In other words, a student might attempt a course, or a student might enroll at an institution, or a student might achieve a particular grade or achieve a particular academic readiness. And you know, again, there is just so much that goes into thinking about how to architect this, and then just when you think you have something, then something comes along and you realize that the graph doesn't really capture it. So there's a lot there. I won't go too much into it. For these transfer students, we have built this knowledge graph, and you know, again, many different elements to it. For what I'm going to show you, this is just a subset of the data. We looked at 7 majors spanning 6 cohorts of students across 8 years. And even at this point, we're talking about graphs that are, you know, 15 million nodes and 39 million edges. And so everything you're doing has to be scalable. I can't show you any actual data or any of the actual analytics that we have done, that we've worked on with Texas Higher Education Coordinating Board, but I do want to give you a sense of why would you spend all this time, why would you spend these years architecting this graph? Well, once you have the system formulated and now implemented computationally as a graph, you can now start to do things like graph transformations, right? All the incredible methods that, by the way, have been developed mostly for the finance industry because people can make a lot of money off representing financial transactions as graphs. Unfortunately, they can't make a whole lot of money of doing the same thing in education, but all those methods would let us do things like selection, projection, aggregation. And you know, what does that mean in terms of education decision makers? Ask questions about longitudinal behavior of students that you just cannot ask if what you're talking about is joining together 100 different databases stored in an Excel spreadsheet. Because students that take classes here and there, different institutions, in and out of enrollment, putting together those longitudinal pathways, but the graph is something that lets you get at that. So some of the questions we have been able to ask and answer, for example, if you look at sequences of 3 classes, what are the sequences of 3 classes that most likely lead to dropout or unsuccessful transfer at some point in the future? And again, that's a question that you just can't really get at with the way that the educational records are stored. So I should probably stop talking, and so I won't go through all this, but again, PGM sits on top of the knowledge graph, so everything is Bayesian. Once we have the graph, we're taking the data. We are now having to learn these conditional probabilities. Everything here is data-driven because there really are no models other than the models that we bring to construct the knowledge graph. But then, as I was just saying, we can start to do these kinds of longitudinal analyses where we are looking at the pathways, and particularly the math classes where if you start looking at the data and the fail rates, it's honestly heartbreaking, absolutely heartbreaking to see how many students are having to pay to take classes, fail them, and then maybe re-enroll and try to take them again the following year. So being able to dig in and understand a little bit about the behaviors, I think is really fantastic. All right, so maybe just the last thing to say, we work together with TAC, by the way, and I guess this is one of the challenges of working in applications that are non-engineering. I think the first 6 months of the project were discussions about how to get the data at TAC so that Lueng could actually access it and we could start to use modern software tools. And like I said, that was about the first 6 months of the program. But a big question is scalability, and what we're seeing here are the times, and just to emphasize the point I already made, the way that the records are stored, and people go in and use things like R to do these analyses, some of these queries, and if you look down these queries, what are the top sequences of courses taken prior to dropout, these longitudinal queries are just not tractable, not computationally tractable, until you have this graphical formulation that really starts to let you make these queries very, very rapidly. All right, so let me close on this slide. This has been a tour from aircraft and spacecraft to cancer patients and then to education. But I hope you all are as excited as I am by digital twins, and particularly the research challenges that I think underlie them. And again, I want to welcome everybody here, and I'm really looking forward to the next couple of days. Thank you.
Let's thank Karen for that wonderful talk. That was great. I think I'll step away from the speakers. And we have time for questions. Yes, actually, Manuel, can you...
Michael, can I interrupt you real quick? Do you mind taking the microphones again?
Just so it's recorded.
That's wonderful work here, and I always love going to meetings so I can finally find out what my colleagues are actually doing. The question I have for you is in the integration of data, which, when you're looping back in, because you're kind of unique position to work in a more, what I would, from my point of view, a traditional area like aerospace and a funky area like medicine. Do you find there are significant differences in how that data stream is handled? Obviously, because there's HIPAA regulations, and every industry and every application has its own issues. And what do you see that as a way to, either an impediment or ways to get around that?
Yeah, no, that's a really important question, Michael. So the integration of data, the way the data is handled, there's so many challenges, and you sort of allude to maybe a difference in maturity or practices in engineering versus medicine, but then if you dive down, it's like every single application in engineering, you're going to find things that are different. I think there are fields that have kind of sorted this out. If we look at control systems as an example, a control system is one where the data sensor acquisition and its role in driving a feedback control system. Of course, this has been well studied, well understood. And to go back to the earlier part of the talk, this is where things like formal methods for verification have a long, rich history and are the reasons that we have aircraft with these flight control systems that are so incredibly safe. So I think there are examples where that has been resolved and is solid. But then you could go and look and also ask the question with the digital twin, often what we're going to be doing is bringing in data sources from different parts of the system that have never been connected before. And so if we think even about the spacecraft system, where what I said about the data is probably true at the subsystem level, right? The propulsion team has really figured out their data and that integration, and then the kinematics, the structures, all these pieces. But now when we start talking about integrating that, okay, at the spacecraft level, yes, we're still probably now in the realm where those questions have been successfully tackled. But what happens when we start now talking about a multi-asset fleet where it's 100 of these spacecraft and we've got the data from the different spacecraft? So that's all a long way to say, I think your question is a great one, and there's just so many layers of complexity. And then when you move into the medicine space, I didn't mention it, but on the slide with Graham's work, that was another one where I don't know how many months of the work was just in trying to get the image data, and I know there are many people in the room who work on these things, so that it talks to each other, so that it also talks to the model, the finite element model, and dealing with all the issues of the data cleaning and the geometry and the mesh. I mean, that took forever. And then you jump to the education, where, like I said, we spent 6 months just trying to figure out how we could access the data not through a web browser, which is how they wanted us to access it. If you could imagine accessing through a web browser and trying to deal with the 70 million nodes on a graph. So I think there's layers there. But big challenges, and really important challenges. Yeah.
Thanks for your talk. When it comes to the knowledge graph side, do you see large language models playing a role in maybe getting more information in those graphs? I know it's already incredibly complicated, but I'm just curious what your take on that is.
No, this is another really interesting question. So, the knowledge graphs. It's funny. I think it's the kind of thing that I have always looked at and been like, why would you need this? But it's because I have always worked in settings where the problem is well defined. And through this education work, I've really come to appreciate, I'm like, okay, now I get it. Now I get why knowledge graphs are such a big thing. I mentioned, Luann and I have worked on different elements of the education problem for about a decade, and going back to when I was at MIT, and we have always architected our graphs by hand. So for example, I used to build graphs of the classes that I taught at MIT, where we built graphs representing all the different learning outcomes and how they map to different elements of the syllabus. Always did that by hand, and always knew that was not scalable because it's just not reasonable. Not every faculty member is going to sit down and spend hours designing a graph that represents their class. So now you come in with large language models, and clearly this is if you could start to automate that. So we have not really worked on that. Luann has a little bit when she is learning the graphs in that education system. It is a little bit of a combination of a little bit of automated learning and a little bit of domain knowledge, sort of architecting the graph. So the short answer to your question is yes, absolutely. I think this is it's a great application. We haven't really worked on it, but. Thinking, of course, but then you have other questions, right? Could you imagine taking all those text files from Texas Higher Education Coordinating Board, feeding them into a giant LLM, and then what would come out? How would you protect privacy? That's a great question. Yeah.
Thanks for a great talk, Karen. It's kind of related to what Emma just asked. Do you think techniques like causal discovery of graphs and what Huma Nawadi works on, hypergraph discovery, right, where you don't know how things are connected to each other and you try and come up with that. Do you think, especially for sort of the second, like the education example, do you think those techniques can play a role here?
Absolutely. And maybe it goes all the way back to the bullseye pictures, which is, so I think absolutely those techniques can play a role. Do we need those techniques to come in and rediscover Navier-Stokes equations or linear elasticity? No, we don't. But in something like the education system, where it is just a pile, like a massive, pile of stuff, and we don't know necessarily what are causal relationships. We know that there are connections. So absolutely. And I think for many problems in the physical world, and I'm sure this is a theme that will come throughout the next 2 days, knowing how to strike that balance between the more, let's call it classical way, where you're injecting the models that you know into the problem versus the, I don't know what to call it, today's flavor of the month, which is just throw it, pretend you don't know anything and see what comes out. How you take the best of those two worlds together so that you're imposing what you know and then learning more pieces. Of course, this is the approach that many in this room are taking, and that's where I think we really need to be. Maybe just the last thing I say is I'm really a little concerned that VVUQ are being left behind with a lot of the work in AI and machine learning and generative models and learning of graphs, because just because you can learn something and then show in some controlled situation that it generates good predictions does not mean you can put it into the real world. And so we have to be very, very careful. It's okay to do that in academia to a point, but when we are coming up with these methods where we know that behind the scenes the hyperparameter tuning has to take place to get the result that we trust, those methods are never going to go into the real world. And so that's why I also believe that the verification, validation, uncertainty quantification have to come in from the beginning, so that if you are learning things, you at least have a sense of robustness, or you can make guarantees.
Can I follow up with it? Actually, the method that the hypergraph of human body uses GPs. So he's got uncertainty propagated everywhere. The problem is, and I was the one who handled his PNAS paper, so I know the paper, is that it doesn't scale very well. So, for example, systems like that, the educational systems that you have, there's no chance. Yeah. It works well in smaller systems, right, that even you don't know actually the physics, you can get good results. I've seen it in some examples we did together, but millions of nodes, I don't think you can do it with the hypergraph.
No, these are huge tensions, right? Interpretability, guarantees, the ability to be able to verify, robustness, and then scalability. But then this is also where you come back to this notion of fit for purpose. In education, we are trying to bring some answers, some data-driven answers to questions that just could not be answered. And so our graphs don't have to be perfect. They just need to be better than the void that is there now. Yeah.
With that, I think we'll close out the keynote session. Thanks again to Karen.